So before I start, let me also thank here all of the collaborations that we have here at ITAMP with Jer and Vasilis. I will not talk about them today, but I would like to thank them very much, and also Stefan, that he is in the audience, and of course Hussein. So today I will briefly present our research results on a collaborative effort with the experiment by the group of Ye-Yun Choi in Korea on the classification of the universal dynamics of a two-dimensional strongly ferromagnetic spinor condensate. So our work appears here in arXiv, and I would like also to thank NSF here at ITAMP for supporting our research, and also many special thanks to all the co-authors that have participated in this work, especially the group of Ye-Yun Choi and his students from the experimental side, but also Hussein here at ITAMP and Kushik Mukherjee at Sweden Lund University. Okay, so let me start with a very brief introduction on why spinor systems are interesting. This will by no means be exhaustive, and it serves only as a very, very preliminary motivation. So gases having spin degrees of freedom provide very fruitful platforms in order to understand magnetic phenomena in atomic systems, since they host a plethora of magnetic phases and related phase transitions. So for instance, here you see, in this talk, I will focus on spin 1 systems. So the total spin will be 1, and I will have, by exerting an external magnetic field, I will split the 3 different hyperfine states of the spin condensate. So I will have the ±1 and the 0 hyperfine level. Okay. So here, what you see is 2 characteristic phase diagrams of these spin 1 gases. On the left, you see, before I say that, I have to say, as Sharon already said in her previous talk, that these spinor gases have both short range, but also spin-spin interactions. Okay, so this spin-spin interaction coefficient is this C1 that I showed you here. This spin-spin interaction can be either positive or negative. Yes, please. Yeah. Right. I don't know. Yeah, thank you. So these spin-spin interactions can be either positive or negative, referring to to anti-ferromagnetic interactions or ferromagnetic interactions. So we have up to now, this is still so we have up to now 2 most used isotopes for these spin 1 gases. This is sodium-23 that has positive spin-spin interactions, or rubidium-87 that has negative spin-spin interactions. And the main characteristic of this is that they feature weak spin-spin interactions. Yeah. So one of the main topics of my today talk is that I will use another isotope which has strong ferromagnetic interactions, and this will motivate more many-body physics, monitor the system experimentally at longer time scales, and also probe correlation phenomena that are not possible with this. Okay, so for instance, here let me focus on rubidium-87, that is a ferromagnetic gas. Yeah. And here you see that so we have 2, from the external magnetic field, we have 2 different tuning parameters. This is the quadratic Zeeman field that you see here in the axis, and also the linear Zeeman field. Okay, by tuning this, that we can do by tuning in the experiment the external magnetic fields, we can really transition between different magnetic phases of matter. For instance, for large quadratic Zeeman coefficients, what we have is a polar phase, which means that all atoms will go and populate only the 0 hyperfine levels, and the ±1 will be unpopulated. As now I tune to smaller quadratic Zeeman, what I will do is to transition via second order transitions. All the green dust lines that you see here refer to second order phase transitions, while the red ones to first order ones. Okay. So I will transition to a broken axisymmetry, or otherwise said in the literature, easy plane phase, where all my hyperfine levels will be populated. And if I further decrease to negative value of the quadratic Simon, I will go depending on the linear Zeeman coefficient, either to ferromagnetic 1 or ferromagnetic 2 state, which means that I will have all my atoms in the +1 state or in the -1 state. Okay. So, and similar arguments also hold for ferromagnetic. Okay. Like sodium 20. Yes, please.
So actually, for such a phase diagram, we assume that the MF equals -1 square and 1 are degenerate, or is there actually?
So here they are degenerate.
Okay.
In this axis when p equals 0. However, here it's not. So here it's only the
So this phase transition is literally like just like an energy sort of argument. Like
yes,
which
exactly.
one of those two is lower?
Exactly. And what I will do in particular in the following is that I will eliminate the effect of the linear Zeeman field, by which I am allowed to do in the mean field level by a unitary transformation. So what I will do is to consider only the quadratic Zeeman, and I will move along this axis. Okay. Okay. So due to these magnetic phases, these spinor gases have been seen a tremendous development in the last years. So it has been shown, for instance, that they can accommodate topological defects like skyrmions, vortices, spin vortices, and so on. Nonlinear excitations, referring to spinor solitons and magnetic solitons that have been also very recently found. They have been shown that we can testify in these systems the Kibitsurek mechanism by dynamically crossing the phase transition, and also because they have different hyperfine levels, we can also examine related spin mixing process. However, another very important and recently developed direction is that to use these gases in order to diagnose quantum phase transitions and also estimate the quantum criticality by means of the relevant critical exponents and so on. A major obstacle up to now, they have been two experiments using rubidium-87. However, as I said before, it's the problem there is that we have weak spin-spin interactions, and we cannot really monitor the gas to long time scale where we see the universal behavior. Okay. In particular, for instance, for rubidium-87, what matters at the end of the day is the ratio between the contact and the spin-spin interactions. So for rubidium is around 1.5%, this ratio. For sodium is 0.48. However, for the lithium-7 that I will talk about today, it's 45%. So it's an order of magnitude. Okay. So a major obstacle was really that we cannot really monitor for long time scales the spin dynamics, and this brought the comparison between theory and experiments that are not in very good agreement. Yeah, regarding also the critical exponents. And of course, another motivation of our work is to classify the universality class of the corresponding dynamical phase transitions that I showed you in the previous paper. Okay. So this brings me to the setup under consideration. So what we will do is to use a quasi-two-dimensional spin-1 gas of lithium-7 atoms. This is the number of atoms of the order of 10 to the 6 that I will use. We have an external optical dipole trap. This is just an external harmonic oscillator in 3 dimensions. Yeah. As I said before, the ratio between spin and short range interaction is 45%, so we have strong spin interactions. And what we will do is to initialize all atoms in the polar phase. So I have all atoms initially in the 0 hyperfine level. And then what I will do is to quench this quadratic Zeeman and go either to the easy plane or the isotropic point here, Q equals 0, or to the easy axis where I have negative quadratic Zeeman coefficient.
So just to be sure here, so you say like spin versus short range interactions. So but the spin interactions, they're not long range. It's just that we have
Short range.
phase. This is kind of short range, like local S-wave
Yes,
scattering,
yes.
and then spin flipping S-wave.
Exactly.
Right. So that's what it calls spin.
Yes. I will show you also. Yes. Exactly. So, and this is done, this quench is achieved in the experiment with a microwave test. Okay, so what we will do is to quench either to this point or to this point, the different phases, and monitor the dynamical evolution of the gas, and then estimate the critical exposure. Okay, so in particular, let me say again that the polar state has only the zero component populated. The isotropic point, I have all the 0 and ±1 states populated. It has an SO3 spin rotation symmetry. While if when I went to the easy axis, this will be the first example that I will discuss now. You have only the ±1 states populated, and it has a Z2 spin inversions. Okay, so let's start the discussion. So on the theoretical side, what I will do in order to compare with the experiment is that I will use a three-dimensional Cross-Pitaevsky equation. These are three coupled Cross-Pitaevsky equations. So you see here, these are vectors F. So you have the kinetic term, you have the external trap, you have the quadratic Riemann coefficient. Fz is just the Pauli matrix. C0 is times n is the density of the system, and C0 is essentially the strength of the short-range contact interactions. And then you have also the spin-dependent interaction coefficient here, where F capital is essentially the spin density of the system. Okay? Then what I will do is to initialize my gas in the polar phase, only the 0 component populated, and then I will linearize this non-linear equation. So I will use these linearization answers, expanding my state from the ground state, mean-field ground state, and then this will be perturbed by epsilon, by parameter epsilon, which is small, and this will be the eigenmodes and the corresponding eigenfrequency. So if I do this diagonalization, I will have this eigenvalue problem for the polar phase. And what I will do then is to use the truncated Wigner answers in order to take both quantum and thermal fluctuations in the initial state into account. Okay? So then I will use my initial mean-field state, which will be perturbed by this noise vector here. And this noise vector here, what it does is that it expands over the eigenmodes of the system, which are weighted by these beta coefficients, where these beta coefficients are taken from a normally distributed Gaussian distribution with 0 mean and unit variance. Yeah. This will be done only in the ±1 components to take quantum fluctuations into account, while in the 0 component, I will use this thermal distribution, and bar J is just the Boltzmann distribution that allows me to take thermal effects into account. And this is done only in the 0 hyperfine level, simply because the experiment detected that only in this level they had thermal fluctuation. Okay. Okay. So what we do is we initialize the state in the polar phase, only the 0 component populated, and went to the easy axis. Easy axis has only the ±1 population. What you see here is during the evolution, the spin populations of the three hyperfine levels. So what you see is that you start from all atoms being in the 0 component, and that during the evolution after the quench, the 0 component loses population and the ±1 takes populations in an equal manner. Okay. So now the very important thing here is that we can categorize all these different time scales in the dynamics into different dynamical features. So the first one, where we see at short time scales almost an exponential decay of the 0 component population, we will have, as I will argue right now, defect formation. So, and in particular here, for a question in an easy axis phase, we have just gauge vortices and anti-vortices appearing in the system. When I create these will start to interact among each other. They will annihilate or drift out of the condensate. And this will create for me the corresponding magnetic domains. These magnetic domains, they will be many initially, they will interact, merge between each other, and finally, I will enter the corresponding coarsening stage where my gas has a universal behavior as I will. Okay. So first of all, let's see what is the vortex nucleation. So here, what I showed.
If I think of wanting to be in the ferromagnetic phase, I would assume that the amount of domain walls is kind of like energetically costly. But then you're saying that the magnetic domain walls are kind of disappearing and merging with one another.
Yes.
So wouldn't that necessarily change the energy of my wave? Like, how should I think of that process? It seems like it's a dissipative process, but you're clearly looking at a quantum gas that's isolated from the environment.
Yes, but I have also dissipation.
Okay, and that dissipation is arising from the outside.
This dissipation arises from three-body recombination. I didn't explain that.
Okay.
Yeah, but I have also this.
And that's kind of where the energy gets like
Yes,
pumped
exactly.
out. Okay, awesome. Thanks.
So here, what you see essentially is different snapshots during the evolution from of the plus in the upper panels and the minus one in the lower panels of the gas starting from a polar phase and quenching to the easy axis. So after quenching, as we saw, plus minus one components take population, and this is what you see here. And in particular, you start to create vortices and anti-vortices in both components. These interact during the dynamics and isolate, some drift out of the condensate. Then you have the emergence of magnetic domains, which finally, in the long time evolution, around 1 second, you end up just with a single domain where between the plus and the minus one components, please.
You previous show us population, yeah?
Yes.
And I didn't see any fluctuation in population. But here, vortices and domains, I thought that reconstruction of them should change population.
This is
Because you have a smooth curve.
you mean here?
Yeah,
Yes. Yeah.
where the fluctuation is maybe not realistic here.
So, okay, so there are very small amplitude fluctuations here that are not seen in this case. Here there are no, because we have really, the gas has been really relaxed.
No, I thought about the vortices, the region when you have a vortices and domains. Right?
Yeah, but this is just the population of each component.
Yeah.
Yeah, yeah.
Why is it not?
It's of the total cloud. It's of the total cloud,
Yeah.
right?
Yes, exactly, the total cloud. So I take the wave function and integrate over x, y, z, and I take just the number of atoms that are in each hyperfine state. You see what I mean? Mhm. No, we have to wait if you want some. Okay, so, and finally end up in a long time evolution with a single domain well between the plus and the minus one component. Okay, so in order to convince you that I did see here vortices and anti-vortices, what I will do now is also to calculate the phase of the wave function. This is what you see here with the for the minus one component for this density. So what you see is essentially here that we can detect phase winding of 2 pi, detecting the gauge vortices. Plus and minus signs here refer to vortex and anti-vortex, so oppositely charged vortices that are isolate. And finally, in the long time evolution, where you have a domain one, you don't see this phase. Okay. Yes, please.
So when you say like the vortices on the plots,
It's this here. So here you see there is a phase jump from 0 to 5. Here, 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 here.
okay, thank you for pointing that out.
Right. So, and then now that we are convinced, I hope, that we have vortices. So what I will do is also to show you the corresponding vortex number during the evolution behaves, and also how the magnetization of the system. So in order to monitor the vortex number, what I will do is to go at each time instant of the evolution in my wave function. I detect at each specific location a phase winding of 2 pi, and I measure the corresponding number of vortices. This is what you see here with the dashed lines. So you see that during the almost exponential transfer of atoms between the different hyperfine levels, you see a very sharp increase in the number of vortices while when they start to annihilate, the number of vortices decreases, and eventually in the coarsening stage tends to 0. Yeah. However, you can see also in the magnetization. So what I plot here with the solid line is the magnetization, and in particular the fluctuations of the magnetization. Magnetization means that I take the oscillation imbalance between the plus and the minus component. I measure this, and then I measure its value here. And peak is just my peak density at the center of my graph. Okay, it's just a normalization. So what you see here is essentially that. And this quantity, of course, will quantify the emergence of magnetic domains. That's why I'm doing that. So initially, it's 0. We don't have any magnetic domains. And as long as the vortices start to decrease, the number of vortices start to decrease, the magnetization starts to grow, while it also oscillates during the evolution. And this oscillation essentially stems from my external harmonic oscillator, because when I do the quench on the quadratic Simeon shift, what I will do is also to induce in my overall cloud a breathing motion, a collective breathing motion. So my cloud will start to expand and contract. Yeah, and this is the imprint here of this collective extension of the cloud. If I didn't have any trap here and I was just in free space, just in a box potential, then all these oscillations will fade away, and I will see just a straight line going like this. Yeah. Okay. Okay. So now that we have an overview of the entire dynamics. So what I will do is also to try to argue a little bit about the scaling of the dynamical scaling of my gas, and in particular its universal behavior. So what I will do first is to monitor the correlation function of the longitudinal magnetization. Yeah. So easy axis, the order parameter of the easy axis is this FZ parameter that I told you before, it's the magnetization. Yeah. Okay, so I will monitor this time resolved magnetization. This is what you see here in this plot, where what you see is as a function of the radial position of the atom, and at different instants, which are marked with the different colors here, you see the corresponding correlation function that it is initially unity and then decreases as the distance becomes larger, it crosses 0 and then goes close to 0. Yeah. So what you see here is that for all different time instants, the correlation function crosses 0. This corresponds to the average domain size of the system. And what I will do is to just rescale this correlation function in terms of the domain size. And if I do that, what I have here is essentially that all of the correlation functions, independent of the time, I mean, for long time instance that vortices have been annihilated, yeah, all on top of each other. Yeah, all the circles correspond to the experimental data. And here you see with the solid line our theory, which are in excellent agreement. So here you see that we see a self-similar behavior in the correlation function, and this indicates the universality of the universal dynamics of it. Okay. So then what I will do is to monitor also how the number of domains scale during the evolution. So the number of domains I calculate from the previous correlation function that I showed you, and it corresponds to the point that it crosses, the correlation function crosses 0. Okay, so what I show you here is essentially during the evolution, the number of domains. Again, the circles correspond to experimental data. Open circles refer to pure experimental data, and the shaded ones are with the deconvolution. yeah, to compensate for the corresponding resolution of in the experiment. So what you see here is, and also then the solid line corresponds to our theoretical data. Yeah, you see a good agreement. However, and you see a good agreement, and I will argue where the corresponding deviations stem from. But the very basic thing first to discuss is that we do a fitting of this domain length in order to identify the corresponding critical exponent, which is 1/z. And if we do that, this is, for instance, the dashed line that you see here, yeah, in the corresponding experimental data. We see from the experiment an critical exponent 0.61, while our theory predicts 0.59. Okay, which are in very good agreement, I hope. So the corresponding differences between theory and experiment are attributed to the experimental resolution, because essentially in the experiment they can go down to 2 micrometers. However, we have seen in theory that there are domains of 1 micrometer and even sometimes smaller ones. So this is the first deviation, the first reason that we can attribute this deviation between theory and experiment. The other thing that I have to say is that in the thermodynamic limit, the prediction of the corresponding critical exponent is 2/3, so 0.66666. Okay, the deviation between our results and the thermodynamic limit now is attributed to finite size effects that are introduced from the trap. Okay, from the external trap. And this we have verified also by eliminating the harmonic trap in the theory side and calculating again the corresponding critical exponent for larger and larger particle numbers. And we see that for increasing particle numbers, you converge eventually to the thermodynamic prediction. Yeah. And now, as I said, so deviations from, you can show from perturbation theory that deviations stem from finite size effect in the critical exponent, and they correspond to there are corrections from the spin healing length that you see here. Okay. Okay, so the next and now finally what I want to say is that in the easy axis phase, the spin 1 gas reduces to a binary fluid, and from this we can conclude that the universal coarsening dynamics here belongs to a binary universality class. Okay, the final thing that I want also to show in order to argue about the universal behavior is also to calculate the corresponding structure factor. This is just the Fourier transformation of the spin correlation function that I told you in the beginning. Here, what you see is that for longer and longer time scales, you see again, both in theory and experiment, that the structure factor for different time instance has a self-similar behavior. So all the data fall on top of each other, both theory and experiment. And then the very important thing here is that for a large momenta, you see that there is a high momentum, universal tail. This is called the Poro tail that has a scaling k to the -3. Yeah, and this linear decay in the correlation function, we have seen that it stems from the linear decay of in the structure factor, it stems from the linear decay of the correlation function due to domain was between the plus and the minus function product. Yes.
Just to make sure, so all these times that you're something there in course name. Right?
Yes, exactly.
Time from their point of view.
Yes, exactly. Yes. Okay, and finally, okay, I told you right now that we have seen this universal behavior. However, whatever I told you now was just for one initial condition. In order to convince you that there is universal behavior, I have to use also different initial conditions and show you that I will have the same result, right? Okay, so what we do here is both experiment and theory. Again, what we do is to use three different initial conditions. So in the first one, what we do is to initialize again in the polar phase the same quadratic Zeeman, but we put an external magnetic field gradient in order to populate only the ±1 component. And then we perform again the quench to the z-axis. In the second experiment, what we do is, again, we start with the same quadratic Riemann in the polar phase, but we imprint also many vortices in the state, in the initial state, and we perform the corresponding quench. And finally, in the third configuration, what we do is to change the initial quadratic Riemann, but lying always again within the polar phase, and we monitor the dynamics. When we do that, here I showed you, for instance, the corresponding scale correlation function. So these different symbols correspond to the different initial configurations, and you see that all of the data fall on top of each other, and we have, and by doing the same analysis in terms of the domain lengths and so on, we can find again the same critical exponent 0.6.
See what is this measurement down, and then after you do the bench, when is this measurement being?
When? In the time domain, you mean, or?
Yes, in the time.
So this is done when we enter the coarsening stage. So we have, yes, exactly. Yes, exactly. In the spin mixing in the first stage, yeah. Yeah. Okay. So now I hope that I have convinced you about the universal character of this dynamics. And finally, do I have time? Okay. So what I want finally is, so whatever I told you up to now is to identify the criticality from the polar to the easy axis vector. Now what I will do is also to do the same quench dynamics, but now quenching to the isotropic pole. Yeah, where there I have a spin SO3 rotation symmetry. Yeah, and also what else do I have? Okay, they have the SO3 rotation symmetry, yes, and the corresponding order parameter of my system is the F perpendicular, which is a superposition of X, of the magnetization in the X and the psi direction. Okay, so all the spin configurations now matter. Yeah. So what I showed you here is the corresponding scale correlation function for different time instants. Both the blue lines is for the X and the red lines is for the Z direction. You see that in all directions, you see this self-similar behavior. So we can argue about the universal behavior, and then we can again monitor the corresponding domain size, where you can see here with the red lines for the X direction, with the blue circles for the Z direction, and we can measure again the critical exponent, both in theory and experiment. We see 0.45 critical exponent in the experiment and 0.40 in the theory. This is again a deviation due to finite size effects. And in the thermodynamic limit, again, we have some finite size effects due to our external. Okay. And finally, I would like here a very important difference between the previous case is that what we see before the coarsening stage is the creation of spin vortices due to the SO3 rotation symmetry. So these spin vortices, for instance, here you can really see. So these are different hyperfine, the densities of different hyperfine levels. This is experiment, this is theory. You see our really nice agreement, and you see also these fork-shaped patterns which indicate the corresponding spin vortices. Where these spin vortices, you can go to the spin order parameter, find each phase, and then you can detect all these spin vortices. However, the very important thing here is that if someone calculates how the behavior during the dynamical behavior of the spin vortices, you will see that they decay inversely proportional to the domain size. And this is very important because this gives rise to diffusive dynamics, and then our universal class changes to a diffusive fluid dynamics. Okay, So with this, I would like to wrap up. So what we have done is to investigate the coarsening dynamics of the quasi-2D spinor 1 gas of lithium atoms, which is strongly ferromagnetic, by dynamically crossing from the polar either to easy axis or the spin isotropic point. We have identified the different stages of the dynamics and the topological defect formation, like gauge vortices in the easy axis and spin vortices in the isotropic point. We have demonstrated the universal behavior of the gas with different observables, like the structure factor of the spin correlation function. We have seen the crucial interplay between the spin vortices in the isotropic point for the critical exponents. And finally, we have classified all these non-equilibrium dynamics based on the order parameter of the post-quench state and the dynamics of the topological defect that emerged before the coarsening state. With this, I would like to thank you very much for your attention.
Hello, are you mentioning two critical points, or are you mentioning
Two.
to
Yes.
across the critical?
No, it's across the critical point.
Across, but not so. The endpoint is not. It's the endpoint you are pointing to.
No, it's deeper than the critical point. Yes. So for instance, here is the first critical point between the polar and the easy plane. I'm quenching here, really deep in the phase. And this is also then the critical point between the easy plane and the easy axis, and I'm quenching here. So it is very deep in the phase.
By the way,
It's not close to the critical point.
we show this collapsing of curves. Have you tried collapsing them when you're attending to different points inside?
No, these are different time instants during the evolution that I showed. So I think you refer to these ones. I'm gaining some time now to think. Okay, I will not do that again. Yes. So all these different colors here refer to different time instants during the evolution. If this is what you are asking. Is this what you are asking?
So
This is time evolution.
time is in that porcelain.
Yes, yes.
I'm just asking for this collapsing. I'm just trying to understand what's the original universality. You have to see universal behavior, right?
Mhm.
It's something. Where does it come from?
The universal dynamics.
Like
Sorry.
Take a naive perspective, I usually associate universality with the critical.
But you cross phase transition, right?
But it doesn't matter which point within the phase you mentioned, so as long as you mention across it, and there's something that's.
In the long. Yes.
So even if you change the endpoints you are mentioning to, let's say.
Yeah, if you go close to the critical point, I'm not sure, I cannot say something.
Maybe an example, you make it like if you sit there and the part of the water, it's kind of like you're not supposed to make certain numbers, but it still always grows at the top.
Mhm.
And that
Yeah, that's a very good example.
Okay.
You mentioned you said that this correlation function and the scaling have the scaling symmetries.
So this here I find in the zero, so this correlation function on different time instants, I check the number, the domain size, and then what I do is essentially to plot this.
You said that it's similar. Similar.
Yes, so self-similar, I mean that it is, it has this universal behavior. So if I scale this correlation function with this domain size, what I see is that for all different time instants, the correlation functions fall on top of each other. This is just what I mean, nothing else.
And the positive and negative correlation function is different for different
So-
for atoms at different distances. So
Yes,
it's correlated
exactly.
and not correlated behavior.
Yes. So that's a very good point. So this crossing and anti-correlation that I see here essentially means that they start to create domain walls between the plus and the minus one component. Because this FZ, this MZ essentially is the population imbalance between the plus and the minus one component, and then I take the value. So this anti-correlation character there means that I start to create really domain walls.
You reach a point where there is something that's social, please somehow correlation, and then because then it goes back to zero, which means
Yes.
the system is no longer established.
Yeah, but this is for large
For that,
distance.
yeah, I understand.
It's
I would
very-
somehow expect that there will be no deepening because it doesn't really change.
Okay. Yeah.
This was something happened that flips the domain wall.
Yeah.
And this one sort of what means is
I think that might be happening because we're doing a punch. And if you were doing this for them at the other, punch, a ramp.
Yeah, this might be, this I'm not sure whether, yeah, for a point on, if you usually go really to the adiabatic limit, I'm not sure whether you have seen this, you will see this. I have not done this simulation, honestly speaking, but then another point would be to see the cubic Zurich for this ramp, which has been seen also recently. They have seen how the cubic Zurich can be testified in this. Yeah.
I was kind of like reasoning because it's a punch, fast punch,
Mhm.
right? Like sudden punch. So you're exciting system.
Yes.
Maybe that's the reason why all those shoes like that and it's flat.
Mm.
There's probably a picture in terms of like conserved magnetization. So because you have a certain number of up and down.
Exactly.
And you have like as you know that overall you have to have domain walls.
Mhm.
So close to you, it has to be aligned as on average you're in the middle of the domain. And then that kind of measures how much you have to travel to.
Exactly, exactly.
domain of the opposite.
Exactly.
This is explain why, like, this services that why it's not being really approaching zero line, but like goes under the zero.
I think like you can probably relate this to like the total magnetization of the system, and if you just have it at being the case, then you have the magnetization be overall positive.
Exactly.
And the fact that like the amplitude is small is probably like a factor of like R in the integral of ER.
Yeah, because that narrow bracket.
You mentioned that during domain phases, you have a damping of the energy because you have 340 energy.
Yes, we have included also this in the calculation. Yes.
The question
But only in
is,
specific.
how is size depends on this if you have
How then?
how damping can influence the dynamics of the domain size.
Yeah, it influences the dynamic of the different size. This is something that we do right now to understand the scaling. That's a good point. But also this will be evident also here at longer time scale.
Yeah, because it's another point which may,
Exactly.
not only size of trip, but this point which may
Yes.
even go
And
down.
for longer time scale, with this three-body recombination, you will see that you will have.
Yeah, even down.
Exactly.
It's like, since that kind of worm is open, like also some. So I guess like the universality might also depend on the kind of damping that you put. So I assume that three body recombination, you're assuming that it's spin independent, and that's
Yes.
why it doesn't affect.
Yeah.
Are there any known like spin dependent effects, and is it known how they could affect like the critical exponent of this?
You mean to have spin-dependent three-body recombination?
But just parametrical, not only if you put in your equation parametrical damping, I don't know what the nature, yeah.
Yes.
You see how it changes dynamics.
Yeah, this is
But
what
just
we are
the-
doing right now
yeah.
to understand. This is what we are doing right now to understand how this dumping affects the features. So I don't have a conclusive answer. What I can say is that you will see a decay in the spin domain at longer evolution time, which they see also in the experiment. Stefan, if you want.
Yeah, my questions were very related.
Oh, okay.
But I mean, actually, my question was, you mentioned, like, when you add these two player recommendations, but, so how do you estimate, like, how strong they are? Like,
So we have the decay.
So, like, if you compare here and like,
Yes, so what we have is that we have experimental data and how the particle number decays during evolution, and we find this coefficient from this fitting.
Parameter. at the bottom of it.
Yes, and this is only observed in the ±1 components in the experiment, so we use only in these spin channels essentially. Quench rapidly. You mean to quench with a finite ramp? To quench with a finite ramp, or rapidly? This is the quench that we do here. This I'm not sure. I have to do the calculation. I cannot say. In principle, I would expect that there will be an effect from a point on, but I cannot really say what will be the ramp that will do that. No, it can be, but it's not here. This is what I'm saying. Yes, yes, sure. It's not here. Okay, thank you so much.
And there's more food.